Hello, my name is Juliette Becker. I'm a current postdoc at Caltech, and today I'm going to talk about getting complete orbital states of exoplanet systems using transit timing variations. There's a few main goals I have for this talk, and this talk is really aimed at researchers who aren't experts at TTVs but are looking to learn more. So the first thing I'm going to go through is an introduction to transit timing variations, so what they are, what they look like in the data. Next, I'll talk about if you want to use transit timing variations to derive masses of exoplanets, what are some considerations that you need to include in your analysis? And then finally, I'll introduce some degeneracies that you get when using TTVs and how you can break those degeneracies. So let's start with a planet in a purely Keplerian orbit. So here I'm showing such a planet. A purely Keplerian orbit means that the orbital period is defined as the amount of time it takes to return to the exact location in the orbit at which the planet started. So what this diagram shows is that the planet will pass in front of the middle of the star at the exact same time every transit event. So if your orbital period is 9 days, then if you observe the star every 9 days on the dot, the planet should be at the exact same place in its orbit. And if that place happens to be transiting, you'll see the planet transit. However, things are not always that simple. So now let's take a look at a not purely Keplerian orbit. You'll see here a diagram that looks the same as before with one main difference. The blue curve representing the planet's flux is occurring slightly or earlier than expected by the Keplerian model. So this is called a transit timing variation, when the exact time at which the transit occurs changes depending on what transit event you're looking at. In the bottom panel of this animation, you'll see the observed minus calculated transit time. So basically how far away from the model is the observed time that you see the transit to occur. The deviations from the Keplerian model are due to extra things that are happening in the system. So what kind of things can cause your transits to deviate from when you expect them to occur and thus cause transit timing variations?
So there are two main sources of transit timing variations. The first is due to star-planet interactions. And there's a variety of reasons that the star will cause a planet's transit to occur later than expected or earlier than expected. These are generally physical parameters about the star itself, such as its general relativistic potential, tides raised on the planet or the star, or the quadrupolar or octupolar potential of the star. Today, we're not going to talk about those reasons. Instead, we're going to talk about planet-planet interactions. Planet-planet interactions can cause transit timing variations because the planets will tug on each other as they orbit, thus causing transits to occur earlier or later than expected. The thing that's really useful about planet-planet interactions causing TTVs is that based on the amplitude of the transit timing variations, you can actually derive parameters about the planets, such as their masses. So let's talk in simple forms about why planets move the way they do. When we think about how planets move, there's one main equation that mediates their accelerations, and that's the classic gravitational force equation. For a single planet with a star, this equation is very simple, and it depends just on the masses of the two bodies as well as their distance separating them. When you start to add additional planets into the system, then each planet-star interaction can be described by one term of this equation that looks just like this. So each of these terms represents the force between a star and a planet, and in isolation, each of these force terms can be used to derive a Keplerian orbit. So the pure Keplerian orbit is derived when you consider only the force between a planet and the host star. However, that's not the only force terms that exist in this physical setup. If there are multiple planets present in a system, then each planet will exert a force on each other planet in the system. And the functional form of this force is exactly the same as what we were looking at before. However, the size of these forces is much smaller than that between the star and any given planet. So each of these terms represent the planet-planet interactions present in a system. If you completely ignore planet-planet interactions and you cross these terms off your equation, then you have a pure Keplerian orbit. But once you add these terms back in, then your orbit becomes slightly non-Keplerian. So what does it mean to have a non-Keplerian orbit? The orbit is still mainly Keplerian. The overall shape looks like it did even before we included the planet-planet interactions in the computation. However, now the effect of planet-planet interactions causes little wiggles in physical space that the planets will exhibit on top of their Keplerian orbits. So these perturbations will manifest in the transit data as transit timing variations, because transits will be tugged slightly earlier or slightly later, depending on where the other planets are in their orbits relative to the one we're looking at in transit. The signatures of planet-planet interactions can be seen in other data types. Transit timing variations are just one way that they manifest in the observational data. However, transit timing variations are somewhat unique in that you can derive not only the standard transit parameters, like the ratio of the radius of the planet to the star, but also non-standard parameters like the planet masses, which you usually need to get additional data using another method. Transit timing variations, because they measure the amplitude of the planet-planet interactions, allow a more complete construction of the state of the system. Now, let's take a look at some examples from the history of using TTVs to infer these parameters. Kepler-9 was the first multi-transiting system that was characterized using TTVs. And here is some of that original discovery data from the Kepler-9 system. So let's zoom in a little bit on Kepler-9c because the transit timing variations are pretty evident. If you take a look at the transit data for Kepler-9c, you see that if you're able to separate the data by color into successive transit events, you can see that some transits are occurring earlier or later. Now, if you know that there's transit timing variations, then you can do a great job characterizing this. If you were not to know that there were transit timing variations in the system, then this would have looked like a really smeared transit, and it would have prevented you from deriving the true physical parameters in the system. So transit timing variations are important for two reasons in transit data. First, you're able to constrain the planet-planet interactions that give you parameters like the mass of the planets, but also you're able to correct your transit photometry and unsmear transit events so you can get a higher signal-to-noise in your complete transit fit. Here is another plot from the original Kepler-9 paper showing the TTV data in a slightly different form. So in the top panel, you have the observed minus calculated transit times. For planet B, they're with blue crosses, and planet C is marked as red dots. These two curves are anti-correlated. What anti-correlated TTVs mean is that the two planet-planet interactions are acting on each other in equal and opposite magnitudes. If there are no additional planets perturbing in the system, then you can both use these TTVs to derive the masses of the planets, but you can also use them to confirm the planetary nature of the candidates. In this way, TTVs can be used to confirm planets which might otherwise only be candidate planets. Here is yet another way to visualize transit timing variation data. So here on the x-axis we have the time at which the photometry was taken, and each row stacked up on top of each other on the y-axis is one transit event taken from the photometry. Baseline photometry is green, while times when less than baseline photometry was recorded are darker blue. There's a clear sinusoidal pattern corresponding to where the transits occur over time, showing that sometimes they occur earlier and sometimes later than the median value. This again is showing planet-planet interactions that are anti-correlated, because if you look at planet B on the left and planet C on the right, you'll see that the signals are perfectly anti-correlated. This anti-correlation is because the signal seen on each planet is due to the other planet in the opposite panel. So again, you can both constrain planet properties and you can confirm the planetary nature of these planet candidates using this kind of data.
Confirming the planetary nature of candidates has been one of the most powerful uses of TTVs, in addition to measuring system properties. Here's an example I worked on, the WASP-47 system. In the WASP-47 system, two of the planets, B and D, exhibit anti-correlated transit timing variations. This allowed us to confirm those planets, even while the innermost planet does not have a discernible TTV signal. Finally, one more example of TTV data. The data I showed you so far was pretty simple. You could look at it by eye, and you could see the anti-correlations present between two planets, and kind of figure out that both planets were real candidates because you detected the gravitational acceleration that they invoked on another planet. And then also you could maybe estimate the masses just by taking the amplitudes of the TTVs. However, transit timing variations will also occur in much more complex systems with more planets. So a great example of this is the TRAPPIST-1 system. Here are TTV curves from Eric et al.'s 2021 paper that uses a large quantity of data over many years to try and constrain the TRAPPIST-1 orbital state. And you'll notice that the curves are not so simple. Some of them appear to be anti-correlated. In particular, you can look at the bottom two panels, TRAPPIST-1E and F, and then TRAPPIST-1G and H. But there's also some additional superpositions of signals going on. This is not so simple to derive, and instead you have to do a large numerical fit to try and extract parameters from these transit timing variations. So the next question is, how do you extract orbital parameters from this TTV data? And the answer is that the model is actually not simple. Planet-planet interactions are very complex and depend very strongly on the many orbital parameters that affect how a planet moves through space, including both the some major axes of all planets in the system, their orbital eccentricities, the direction of their line of nodes, as well as other parameters. When I say this is a complex problem, I mean it's a problem that's not only hard to solve, but it also has a lot of degeneracy. So let's walk through what some different orbital parameters do to a TTV curve. So here's a baseline model of some TTVs of KOI 125b, which is a planet that has an exterior non-transiting companion. This is the correct, quote, quote, model of this planet. But let's take a look at what happens to the model when we change some of the parameters. We'll start first with the period ratio. So in this animation, I'm looping over period ratios of the outer to inner planet period. And what you'll notice is that as the period ratio approaches values close to mean motion resonances, then the amplitude of the transit timing variation signal becomes much larger. As you get further and further away from these resonances, as is about to happen here, then you get much smaller TTV signals. So as you can see, a very small change in orbital period can have drastic impacts on the amplitude of the observed TTV signal. The exact same thing is true for the orbital orientation of the planets. So here I'm plotting delta omega, which is the difference between the argument of periastron for the inner and outer planets. And as I cycle through the entire range of 0 to 360 degrees, you can see that the exact amplitude of the TTV changes, not as drastically as it did for the orbital period ratio, but still enough that if you're trying to determine what delta omega is from a fit, you'll have some degeneracy in your solution with that and the previous values. Here is another plot, this time for orbital eccentricity of the inner planet. And as you increase the orbital eccentricity of the inner planet, again, holding all other parameters for both planets fixed, then you'll notice that the TTV amplitude increases. Finally, next up, we're going to look at the mass of the perturbing planet. The perturbing planet is what's physically causing the variations in transit time that we're observing in the aqua curve. Here, when you increase the mass of that perturbing companion, you also increase the amplitude of the transit timing variation itself. So, as these four previous animations have shown, there's a lot of ways to increase the transit timing variations that you observe for a system. So let's now go through a summarizing list of what are the factors that cause these TTV amplitudes to be larger. First of all is the masses of objects in the system. So if planets are larger or if the star is smaller, then the TTV amplitude will be larger. The reason for this is that for TTV signals to be larger, the planet-planet interaction terms need to be more important than the Keplerian term, which is the term between the star and the planet we're looking at. And this occurs if you have either larger perturbing planets, which can exhibit larger accelerations on the planet you're looking at, or a smaller star, because then that Keplerian term is weaker. The next thing that can increase the TTV signal is if planets pass closer to each other in physical space. So remember that that force expression we were looking at earlier depended on r to the -2. So if r is smaller, then, and this may occur if either planets are in resonance, so they will have conjunctions at the same point and periodically pass closer to each other, or if their average distances are smaller. Then in either of these cases, you might have larger transit timing variations. Next up, all other factors held constant, the TTV will increase if the orbital period of a planet is larger. And that is something you couldn't see in the animations I just showed, but it's a general statement that's true. And then finally, the orbital eccentricities will also potentially cause planet-planet interactions to be stronger and the TTV signal to subsequently be stronger as well. I will note that this is not a simple scaling. Although I showed a plot on the previous section of the eccentricity increasing the TTV amplitude, the piece of information that actually causes the TTV amplitude to increase is the combination of E cosine omega and E sine omega, when omega is again the argument of periastron. So for orbital eccentricities, it's really some combination of eccentricity and omega that's causing the TTV signal to be larger. But in general, larger orbital eccentricities will cause larger TTVs. So if all of these different factors will cause increased TTV signals, how can you tell them apart? This is one of the biggest issues with using TTVs to derive planet parameters, is there's a lot of degeneracy between all of the factors that I'm listing on this slide. So now let's take a look at degeneracy in action. One really good example of how confusing these degenerate parameters can be comes from Sarah Ballard's 2011 paper on Kepler 19b and c. So you can see the transit timing variations derived from Kepler data on the left panel. Now, these transit timing variations are large enough that they indicate the presence of an additional planet, Kepler 19c. However, despite the fact that they indicate the presence of a planet, you cannot uniquely constrain the parameters of the planet quite so easily. In the right panel, you see all the potential orbits for the companion that the authors of this paper computed were consistent with the signal of the TTVs that you see. And the reason for that comes from all those animations I showed. If you increase different values, whether it's the period ratio, the eccentricity, the alignment in angular space, or the mass of the companion planet, all those factors can increase the TTV in very similar ways. So this degeneracy is very limiting. Degeneracy can potentially prevent you from understanding the states of systems you're observing. The next goal is, of course, to try and solve it. So how do you solve this degeneracy? There's actually a few ways. So one way to help solve this degeneracy is to, instead of using only transit timing variations, to also look at the transit duration variations. So transit duration variation is, instead of looking at the exact center of the transit, you're looking at the amount of time that it takes for the planet to transverse the chord across the star, and then looking at how that amount of time varies with time. Very similar to transit timing variations in terms of both causes and what it's going to look like, but technically a different signal. So it does help solve the degeneracy to some extent. Another way to try to solve this would be to use the TTV chopping signal. So the TTV chopping signal is a short period signal that depends only on the planet masses rather than the eccentricities. And so if you can find the chopping signal in addition to the sinusoidal overall TTV signal, then you can get some independent measure on the mass as well as the mass and eccentricity. And then you can detangle those to try and find independent constraints on mass. Finally, the option that solves almost any problem in observational astronomy is more data. So the more data you have, the better a solution you can construct. And this is both true if you get additional types of data, such as adding radial velocity data to your TTV data set, or if you get additional transit data from many years later or from another source. So these three methods each have their own way of helping solve this degeneracy that's inherent in the TTV data. So looking at transit duration variations is one way to attempt to resolve these degeneracies. Here I'm showing a river plot from the 2013 paper on KOI 142b. And you can see from this river plot that there are some relatively high amplitude TTVs on this planet. However, the TTVs are not the only thing that changes with time. From the same paper, you can see here on the top panel is the TTVs and the bottom panel is the transit duration variations. Although the amplitude of duration variations is generally smaller than it is for the transit timing variations, the durations change due to a different combination of parameters. So the dominating factor controlling the chord a planet takes across the star is the orbital inclination, but the sub-major axis eccentricity and argument of periastron will also matter. And so if you fit transit timing variations and transit duration variations simultaneously, then you can potentially get a better solution than you can with TTVs alone. The potential difficulty of this is that TTVs can be difficult to measure, especially if your data is not particularly high cadence. But if you can get both TTVs and TDVs from your data, this is a great method to try and dial down on some of that degeneracy. The next method to eliminate degeneracy is extremely powerful. So this is the chopping signal. So here I show a paper from Kat Deck and Eric Egal's 2015 paper where they derived the equations for this short period chopping signal. The overall transit timing variation signal is a combination of various components, one of which is a large amplitude sinusoidal component that is generally the dominant term you see when you look at these plots. However, there is additionally a short period term, much smaller in amplitude, shown here as the red points with the model being a blue sinusoid, that you can see if you correctly subtract off the sinusoid of the large amplitude term. If you can fit for this term, the strength of the chopping signal depends on the true masses of the planets, and this allows you to break the degeneracy that's inherent in normal TTV fits. So if you have data of sufficient quality and precision that you can resolve this chopping term, you could get true measures of the masses of the planets. So let's take a look at when this has been done in the data. There's a couple really great recent examples of where this chopping signal has been used to successfully retrieve the masses of planets. So let's now return right back to the KOI 142 system. So this was a system where the inner planet was observed to transit and had really large amplitude TTVs. So this is KOI 142b. There were not immediately any other planets seen in the system, but these large amplitude TTVs did indicate there was an additional unseen planet present, and the amplitude allowed an estimation of the orbit and the mass. But there's something else you can do with a system like this, where the amplitude of the TTVs is so much greater than the precision. It's a perfect test case for the chopping signal. So I'm now showing a figure from Weiss et al. 2020, which is the same river plot and shows the transits of Kepler 88b, which is KOI 142b. And again, you can really clearly see the signal that's due to the perturbing planet, which is Kepler 88c. If we take a look at this data presented in a slightly different way, so in the top panel, the river plot is replotted as the amplitude of the TTV at each transit event. And you can see that if you fit a polynomial to this, then you get a pretty good fit to the TTV signal over the Kepler baseline. In the middle panel of this plot, you can see what happens if you subtract that fitted polynomial. What you're left with is actually the chopping signal itself. And the blue is the observed data. The orange is the best model from TTVS, which is the code based on Kat Deck and Eric Egal's 2014 and 2015 papers on the chopping effect. And this allows you to uniquely recover the masses of the planets involved in this planet-planet interaction. You can only do this because the TTV amplitude is so large, which makes the chopping amplitude detectable. But you can see that the chopping model does a really good job at reproducing the signal left over once you subtract the overall polynomial. Now let's also take a look back at TRAPPIST-1. Remember how I mentioned before when we looked at this plot that although you could see some anti-correlations in the bottom couple panels, the signal overall looked quite complicated. And if you look at the blue and green models in the top two panels of this plot, there are some short period oscillations that you would not be able to expect by eye. Now, what are these short period oscillations in the TRAPPIST-1 data? These are, in fact, the chopping signal. If you look here at these plots, one per planet in the TRAPPIST-1 system, again, the large amplitude polynomial has been subtracted off of the TTV signal, and you're left with just the chopping signal. Some of these signals look more convincing than others. In particular, if you look at the outer three planets, the overlap between the model and the data is quite good. For the inner planets, the data has sufficiently large errors that although you can perform the optimization fit, it's not as strong a signal. You can use a large fit like this that incorporates both the overall polynomial as well as the short period small amplitude chopping effects to get better constraints on mass. Basically, if you have enough data to do this kind of fit, you're going to get better results than if you try to fit only the overall sinusoidal terms alone. So let's summarize that conclusion. The chopping signal, a short period variation in transit time that depends primarily on the planet masses will give you distinct constraints on mass and eccentricity that you cannot get if you don't have that signal. So if you're trying to do a TTV fit, I highly recommend you check and see if you have the chopping signal present in your data and if your transit precision is good enough that you'll be able to resolve it. There's an expression in CatDec's 2015 paper that gives you the expected precision you'll need to constrain the chopping signal for whatever system you have. Now, the final method I mentioned as being useful for breaking these degeneracies is more data. So now let's move on and talk about TESS and transit timing variations. TESS is a uniquely powerful tool to better understanding systems with transit timing variations. Despite that, I will start with some of the challenges with using TESS for transit timing variations. The main challenges for using TESS data to better understand these systems that either are already known to have TTVs or found to have TTVs is the baselines. So there are both gaps in data, and also the baselines for some stars are not very long. And this means that compared to Kepler, you're going to have a harder time getting a continuous time series of TTVs. However, there are two gigantic benefits that TESS has. One is that the baseline can be humongously extended compared to systems with only Kepler data, since it's been many years since the Kepler data was taken. So if stars are reobserved with TESS where there's already Kepler data, you could do a great job constraining what the true orbital states of those systems are. Secondarily, the targets are a lot brighter. So why does targets being brighter matter? The reason is I mentioned that to do the best you can on TTVs, you want to combine your TTV data with additional types of data. For Kepler, a lot of the stars were too faint to study with radial velocities. Since TESS stars are bright, this is no longer an issue. Here's a great example of the power of combining TESS photometry with additional observations with other methods. So this is the TI 216 system published by Becky Dawson this year. And you see on the left is all the transits that were observed with various instruments. So TESS are the red points. There's the most of those, especially for planet B. This transit data, these derived TTVs that come from all of these different photometric data sources, can be combined with radial velocity observations, see on the right, to do a more powerful fit that more strongly will constrain both the orbital state of the system as well as the masses of the planets. So this is a very powerful thing that you can do with TESS data since it's bright enough that you can get these follow-up radial velocity measurements. Now, in addition to these targets being bright, I mentioned that you could also extend the baseline of previously discovered sources. Here is a plot from Max Goldberg's 2019 paper showing the power that additional transit events observed with TESS has on improving solutions that were originally derived with Kepler data. So here you can see how two solutions diverge. Both solutions were consistent with the Kepler data at early times. But the low mass and high mass models diverge quite strongly as time goes on. Since it's been many years since Kepler took this data and those solutions were computed, additional TESS constraints can improve our precision on those measurements by differentiating between models, like the case shown here. In that way, the long baseline of TESS provides a unique way to improve our knowledge of the Kepler multi-transiting TTV systems. There is not enough time in this talk to go through all of the wonderful TTV results that have been found with TESS so far. So instead of going through them in depth, I'm just going to put some TTV results from TESS up on the screen. Some of the characteristic results from TESS include both system solutions, where you constrain the orbital states of the planets using TTVs, as well as insights on additional planets present in the system. At times, the limited baseline of TESS has prevented a true measure of the TTV amplitude, but since TESS targets are bright, this is something that follow-up observations will be able to continue to constrain. So now I will end with a summary of the main takeaway points. First of all, TTVs can confirm planets. If you have planet candidates in a system that have anti-correlated TTVs, you can use this as evidence that the planet is real and use it to confirm the planet. Secondarily, TTVs can discover new planets. So in many systems where a TTV signal was present, but the culprit of the system was not seen, the TTV signal can be used as evidence of the presence of an additional planet. Finally, when you do a complete orbital fit, including both the overall sinusoidal TTV signal along with the chopping signal, you can get a complete orbital state of the system, including the masses, the arguments of pericenter, and the eccentricities. This is not an easy fit to do, but the codes that exist to attack this problem have grown with complexity and effectiveness as the years go by. So you can actually do pretty well fitting TTV data using open source tools. Finally, if you're interested in learning more about TTVs, I've listed 5 papers that would be a pretty good start. So I'll leave this up for a few seconds. Feel free to pause and copy down some of these bibliography codes. But thanks so much for joining me and talking about TTVs today.